I'd like to welcome Daniel Neumann, and who's applied to join us. And finally, we're going to get a rings person back. Since Joe Spadali was with us before. So I don't know if you know Joe. So I'll hand it over to you, Daniel, and you start off by telling a little about yourself, and then take it on.
Okay. Thank you everyone for coming. I'll be presenting. Most of what I'll be presenting is my PhD work, which I graduated. I did this in last at CU Boulder and graduated last year. Well, my bachelor's was in Venezuela, so I'm Venezuelan. Although currently I'm living in Panama City. Well, that's all I want to say about myself. Let's begin talking about my work. So the bulk of my work in the PhD had to do with waves in rings. And this is an old topic, of course, but most of the work has actually gone to studying density waves. And I think people know density waves very good. But bending waves are actually more of an obscure topic. And I think there's a certain assumption, because the math bit of the two theories is very similar, that physically they're going to behave similarly, but what we're finding here is that that's not true. So you can just hit the bending waves with the same hammer that you hit the density waves. And particularly these two waves here are a good example because they're in the same region of the ring. And if you use them to measure different properties, you get different answers. And we're going to talk about that and what that might imply. So stepping away a little bit from the rings, bending waves and just warps in general are becoming more and more important to understand astrophysical disks. Of course, rings is one example of them, but we also are seeing debris disks that are a little bit bent with respect to the plane of the planets. Actually, there's even a possibility that the Kuiper belt it's like that. And also, recent protoplanetary disks show shadows that indicate that there's a warp inner disk. So that's also something very prevalent. And that happens when the star has some obliquity with respect to the ring, which is maybe more common than we think. In galaxies, there's also a recent dramatic advancement that we now know that the Milky Way, this is not the Milky Way, but we now know that Milky Way is warped. It's not in equilibrium. And also just galactic sensors have shown that it's actually the most common thing for disk galaxies to be warped. And we don't understand how the warp propagates, how it's maintained, because in the case of galaxies, for example, it shoot up fairly quickly. So we think maybe it's maintained by the dark matter halo or something. So there's a lot of questions. And a place where we can start asking those questions are the fundamentals of how these things work is in the rings, because we have a lot of data of these waves. And this animation here represents our knowledge since the 80s of these bending waves. And actually, the bending wave theory applied to Saturn is on a Shu paper, 1983, Shu, Kusi, and Lissauer. It's just directly imported from the galactic people. So there's a collaboration between these two communities from the beginning of studying bending waves in general. But the ring has a particular advantage of having a lot of good resolution and data. So how exactly do we measure the waves in the rings? Well, we use occultations. So we look at a star, and as the light crosses the ring, it will attenuate the light at different intensities. And that's going to tell you about what the geometry is. So here's an example. If you're looking at that star, and Cassini is navigating, and it's going to look at decreasing optical depth when the warp and the line of sight are more or less perpendicular. And then when the warp and the line of sight align, there's going to be a peak. So the prediction here in this top figure is from the Shoe theory, is created by using the Shoe theory for bending waves. This prediction is that you're gonna see that sort of pattern, right? And again, this warp in the case of planetary rings is caused by satellites. I show you at the first slide. There's a picture of satellite that's Mimas. So this is a bending wave caused by Mimas. And there's a resonance. It's a resonant phenomenon. So that's why it's maintained over time. Note that the top figure here, the scale, watch out for the scales of these things, because the warps are actually for these perturbations are like 15 degrees at most, 20 degrees at most, sometimes less. So the slopes are actually very small. So I have to exaggerate them. So obviously this is not to scale the X and the Y here. So this is what we see. This red line here is what we see, and I'm comparing to the Shoe theory. And there's some things that pop up. For me, the fact that the theory predicts that there should be some places where the optical depth decreases with respect to the flat ring, and that we don't see that anywhere. And also, well, if you use the viscosity obtained by measuring the density waves and just the viscosity that we think that governs the collisions and the dissipation of angular momentum in the ring, of energy, in the ring, and the angular momentum transport, then that would indicate that the wave should extend more than what we see. So the wave is kind of overdamped relative to what the theory says. And at the beginning, we also see that the first peaks are higher than the theory predicts. Now, this is for an oblique occultation. So you're gonna get all these variations in the optical depth if the star has a low opening angle with respect to the ring. So here on the top right, I have a little bit of a cartoon showing kind of, if this is the ring plane, you kind of have to be, the star has to be close to the plane when you look at it in order to get these variations. But in theory, or according to the Shoe theory at least, if you have a star that is right on top of the rings, then you should just see a straight line. You should see no variation, because the theory predicts, opposite from the density wave theory, this theory predicts that there should be no density variations. It's just a warp, but the density itself of particles don't change. And
Daniel?
yes,
Mind my asking question here?
sure.
I don't quite understand your statement, because, if these things are, if the density is unchanging, and like the width of the stuff, or like if it looks like what you've actually drawn, which is a line that has a equal width, unless that line is thinning out in places and then thickening up, say at the top and bottom, then you're still going to be going through more material when you're looking along the side straight down than when you're looking across the top. So is there some attenuation of the ring, at least in width or something like that?
There's some thinning, like you said, if you think about thickness as, so if you think about vertical thickness, so it's just the difference in the C coordinates for the upper and the lower part of the ring, for example, that doesn't change. So the vertical thickness is uniform.
Okay.
But yes, but there will be a change in thickness, kind of like if you go perpendicularly when you have the big slopes.
Yeah.
That will, but this is in theory a perfectly vertical occultation. So you only see the vertical thickness, which doesn't change. So the thin ring, which by the way, the A ring and just the rings in general are very thin. We are thinking about 10 meters thickness. So if I were in an auditorium, just from the floor to the ceiling, will be the thickness of the rings.
Mhm.
That doesn't change, right? And it is, maybe you're skeptical about it, and we are going to see that this assumption is actually something that is breaking down. Because you have this warp that is a kilometer in amplitude, and you have this that is 10 meters in thickness, and it's being warped 1 kilometer. So that's very impressive.
That's amazing. Yeah.
Yeah.
Yeah. Thank you. Thank you.
Yes. So yeah, the vertical thickness doesn't change. Otherwise, the kind of like the thickness, let's say perpendicular thickness does change. It's like Mark remarked. So okay, the theory is that the thickness doesn't change. Also, there's no change in density. So you have a flat line. What we actually get is this increase in optical depth. And I think this is the biggest discrepancy, right? Because in the previous oblique occultation comparison, there were some things that were wrong, but there were also things that were more or less right. Here, it's just missing the mark completely. And we want to emphasize in understanding what's happening in these normal occultations. So our first question was, well, what explains this extra optical length? So what's going on here? What's causing this? And we found out that it has to do with our gravity waves. So a little bit of a recap. So gravity waves were posited as a mechanism in the 70s, actually, to explain what ring scientists call azimuthal brightness asymmetry. And that's something you can see in this picture where the brightness of the rings has some azimuthal variation. For example, here on the top left, it looks a little bit brighter than on the top right or on the bottom. And that has to do with the fact that the ring is made of these filaments structure that happen due to self-gravity, and that they are oriented coherently at 23 degrees. And their scale, by the way, the scale of this microstructure is about 200 meters. So this is the Toomre wavelength, actually, is what you should expect for the length and their separation also. Or on the order of. So here's a simulation that shows the formation of these gravity waves. And the interesting part of the simulation is that once, like, if you give it an orbit and you start uniformly, it very easily creates these structures. And this type of Shear-box simulations are really our best tool to understand the physics of gravity waves, because in terms of observations, most of what we've seen is really just the azimuthal brightness asymmetry I just showed. But their dynamical properties are better studied by this type of simulations. And these simulations are very complicated. So we still see that there's this coherent orientation, but really, why 23 degrees? Right? Why exactly that orientation? People usually explain these gravity waves as a phenomena that it's also understood from galaxies, which is why they call it gravity waves. This is a figure from Julian Toomre in 1966, where he shows that if you have some overdensity here, the stars are going to spend more time close to that overdensity of the disk, and then they're going to create this overdensity pattern. But the stars never actually come together or anything, so that's why it's kind of like awake. In the case of the rings, however, these things come apart. I'm sorry, come together. They come apart also. They come together and they come apart in the period in one orbital period. But they're more like, if you look at it in timescales shorter than an orbital period, they're actually kind of orbiting together like a very transient satellite. And that's a big difference. The prediction for the theory for Julian Toomre, by the way, for what the angle should be for a Keplerian disk is 12 degrees. So there's that question of why 23 that is unanswered. And I had to answer this in order to go back and actually solve the bending wave problem. So this is a little bit of a detour that I had to do. So, like I said, if we're looking at time frames that are smaller, this behaves more like a satellite. And we took that seriously, and we approximated these gravity waves as rigid bars, specifically rigid granola bars. So to make our life easier, also there are parallelepiped in nature. So, and now that you have this rigid body, you're gonna have different torques. In the case of the flat ring, the important torques are the tidal torque, which is aligning the long axis with the planet. And also, if you're aligning with the planet and you have a Capellian shear, there's going to be collisions due to the particles in the Capellian shear. And that's going to want to align the long axis with the azimuth. So there's a question of, is there an equilibrium angle? And the answer is yes, there is an equilibrium angle. If we balance these two torques, this is the equation for the equilibrium angle here. Here in the theta will be the equilibrium angle for the zero gravity of these two interactions, moving that equilibrium angle. On the left, we have the tidal torque, which will depend on the mass of Saturn. It depends also on the dimensions, H, L, and W of the zero gravity wave. And then the collisional torque due to the Capellian shear is going to depend on how much things are between zero gravity waves, the coefficient of restitution, and the shear rate. So it is what you will expect, and we can test if this is a stable equilibrium situation. It is. And also we can talk about relaxation times, and actually if you move away from equilibrium, you're going to go back to equilibrium in 0.2 orbital period. So the time scales work in terms of assuming that this is kind of like instantaneously rigid, because the lifetime of these things is about 1 period. They can last even 2 periods, but on average is 1 period. And the simplicity of the approximation even allows us to write down a potential and a potential world for the equilibrium, and we see that it's a stable equilibrium. We can compare this model to the Shear-box and body simulations. Particularly, we can compare how the equilibrium angle changes with the shear rate. So the stronger the shear, in theory, then the smaller the equilibrium angle, because it's more azimuthal. And the lower the shear, the more radial. And here on black is our model equilibrating the torques. The green is a model that is even a further simplification of that. And the triangles are the n-body Shear-box simulations. We capture some of the physics, particularly with the black one. So we are confident that now we can study the motion of zero gravity waves in bending waves using the same method. So back to bending waves. Now we're going to kind of insert the zero gravity waves in the system. And we do that by first, we draw the zero velocity curves of the zero gravity wave. So we have to compute all of the collisions I just mentioned. We're doing that numerically by using the Hill problem, right? So here is kind of like the Hill problem for the wake, where the wake is this black thing. It's just a bar. And we're going to have the tidal and the Capellian torques. But now we're also going to have torque due to the bending wave, a vertical torque, because there's going to be also collisions that are kind of north-south. And also wakes are going to interact with one another gravitationally, and we include all of these torques and compute what the motion is by integrating the rigid motion equations, right? So these torques we computed for all the coordinates, and then just plug it in here, tau x, tau y, tau c, and then integrate those equations and get some motion. And here's a cartoon that more or less explains what we find. So the most important thing is that this rotation actually causes a difference in the velocities of the surrounding particles and the waves as they move up and down. So that causes collisions, and the collisions are significant. So there are, for the rings, if you have centimeter per second collision, 5 centimeter per second collisions, that's significant, and you should expect some regolith to form. And furthermore, not only do we find that there's these velocities that can be releasing material from the subgravity waves, but also the kinetic energy of these impacts is proportional to the slope of the wave. And if the number of particles is proportional to the kinetic energy, then we find this relationship that we can test empirically, which is that the number of haze particles, and haze we're calling this ejecta that is going to create the signal, excess signal that we see in the occultations. So that signal is going to be dependent on the amplitude of the slope of the wave. So the more the warp, the more signal you're going to see. And this is another thing that we're finding from the dynamics is that the collisions are actually very frequent. So maybe they happen 10 times every period. And hence you always have particles flying around at any point. So there's kind of an envelope surrounding the wave that is created by these smaller particles. And here are the consequences if we follow the trajectory of those ejecta. This is how it's going to look like. So the blue fill is the haze of particles, and it has some interesting geometrical properties. For example, the vertical thickness is no longer constant in this case, and that's going to have some observational signatures that we're actually going to find in the signal. So to test this against the data, we do a ray tracing code. And we predict that, among other things, there's going to be this signal that's going to peak with the slope, but also there's going to be the kind of like the basis of those peaks in the subgravity wave should be broader than the theory, because that's the effect of having this variable thickness envelope. So does this match? Well, here is the same occultation I showed before. In green is the shoe theory, and the black is our best model, which is we include that extra layer of particles. And the first thing I want to notice that indeed the thickness, if you look at the thickness of the bases, it's changing between the two models, and the black model matches the shape a little bit better. Particularly, like this shape is actually matched pretty good. So that's good news. And this is something we were not expecting. We were trying to get the enhancement, the normal optical depth. Now, we also find that we can increase viscosity is a free parameter here, so we can increase it. And we believe that this increase in viscosity has to do with the subgravity waves interacting in this way and sharing the material. And when we look at the normal occultation, well, we also find that the peaks of the slope and the peak of the signal more or less match. The shape is not perfect, but it is interesting that the location of the peaks is very close, because the location of the peak is sensitive to the viscosity. So the viscosity that fits the damping length of the wave is also giving us the right location of this peak, which is a good indication that there's a relationship between the slope and the signal as we predict there is. Now, there may be implications for this higher viscosity. So the viscosity is increasing almost a factor of 2. Well, a factor of kind of like 1.8 with respect to what we thought before and what we see in the Prometheus density waves. So there's a rather sharp radial gradient in the viscosity. And a consequence of this could be that material is being transported radially outwards from the bending wave. Normally, we think about viscosity, particularly in planar formation, we think about viscosity as something that closes gaps. But if you have this type of radial gradients, you can have this radial transport happening, and you can have gaps being partially open. And when we look at our surface density for our bending wave, our study and also previous studies for that bending wave, which there was one by Gresh, by Donna Gresh, says that the density is higher, 25%, in the density wave, in the Prometheus density wave, than in the bending wave. So the density in the bending wave is already lower than the surrounding areas according to other measurements. And maybe this is due to the fact that there is this increase in viscosity, so particles are going to be moving radially. Another thing that we should expect from this mechanism, as I mentioned briefly, is that the signal of these things, the particle size of the material that creates the optical depth should be smaller, because in theory it's being released from the surface of the gravity waves, which simulations like the N-body simulation that I showed show that smaller particles tend to accrete into the surface of bigger particles, and that's also true for the gravity wave, where it's mostly bigger particles closer to the center than the smaller particles. And if we do a multi-wavelength analysis using radio in this case, we have the S-band that is kind of like 10 centimeters, and the K and the X-band that is 1 and 5. And we see that the S-band is not seeing something that the other two smaller wavelengths are seeing. So, and that difference doesn't exist outside over here. So it may be, so this is also consistent with the fact that this hump is created by smaller particles, which is explained by the mechanism that we're proposing. So that concludes what I did for the PhD. But now I want to talk about what I'm currently doing now. Let me see how much time I have. Okay. So there's 3 other bending waves that I want to study, and then I have been studying since I graduated. And I have it here in order of how interesting they are to me. The first 2 are the 0 to minus 1 bending wave, which is a weird name, but the reason we call them that is because it's not the vertical frequency of the satellite resonating with the mean motion of the ring particle, which is what happened in the Mimas 5-3 case, but it is the precession of the ascending node resonating with the vertical frequency of the satellite. And the precession of the ascending node goes the other way, so retrograde, and that's why there's a minus 1. So it's a bit strange, but it works out mathematically that this is that type of resonance. So the Iapetus bending wave, as I said, is the most interesting one. And one of the big difference with respect to the other ones is that the amplitude of the wave, so the warp, is actually on the order of the thickness. So this is a very weak bending wave. It's hard to see because as I show you, the variations of the optical depth in oblique occultations has to do with the warp, but if the warp is so tenuous, then it will be hard to see. So in order to see them, we applied a wavelength analysis, so really try to look for this using a lot of the data set, not just one occultation. And here is an example of what we should see if the only reason for optical depth variance is this wave. So this is the model of the wave on the bottom, is in terms of counts instead of optical depth. And you see there's a very small, maybe 5% difference in the counts due to that. And in reality, the variance, the noise of the data is in the same order. So we really have to hunt for this signal. And when doing this type of analysis where we're hunting for a particular frequency, this is kind of like a localized Fourier analysis. We do see that there's this peak in the frequency that we were looking for, or in the wavelength, sorry, in this case, that we're looking for. So this is a detection in occultations, but you see, it's very hard. This is how the data looks on the bottom. It's very different from the Mimas that was very clean. So the best way to study this bending wave, there may be something interesting here looking at these occultations, but by far the best way to study them is by looking at this particular picture. Here, the bending wave appears clearly on the left of the picture. All of these undulations are the waves. And the reason this is so is because this was taken during equinox. And during equinox, the sun is basically, etch on the ring. And any corrugation in the ring, any vertical structure gets very amplified. And that's why it just appears. And the first thing that catches my eye from this picture is how long this bending wave is. So the Mimas bending wave was 200 kilometers. In this wave, somehow manages to propagate 4,000 kilometers. Here is, if you add, the pixel values of that picture, azimuthally, you get this plot on the bottom, and you see that the quality of the signal is very good. And you also see, going back to the most impressive thing for me is how long this is. And this is the Mimas bending wave. The entire Mimas bending wave is just one wavelength. And another thing that we see that is very interesting is that here there's a boundary that shows that there's an increase in surface density. And the way we know this is because the wavelength is dependent on surface density. And the wavelength should become shorter and shorter as you move away from resonance. Here, resonance happens here. But here, there's a sudden increase in bending wave. And we go and compute what the sigma is, there's actually an increase in sigma. And this is what we think is what's called the inner A ring, because the location of this is very close to the inner A ring. And there's a sudden slight ramp in sigma called the Cassini ramp, because we're moving away from the Cassini division and into the A ring. And then there's kind of like a sharp edge. And this is actually a sharp edge in sigma. And it's very interesting that you can see it in the wave itself. Here is another, this is the data, right? Here I'm plotting the wave as I think it should look given the data. And there's this boundary where there's this sharp cutoff or change in sigma. And it somehow propagates forever. Here already at the end, this amplitude is actually, here the thickness of the ring is really thin. It's thinner than it should be because the ring is, like I said, 10 meters. So at the end, the amplitude of the wave is similar to the thickness. So we shouldn't be able to see. And this is without any viscosity. There's a because the sigma is increasing, that also changes, as you can see here, that also changes the amplitude. So just changes in amplitude due to the surface density are going to already make this damp in 4,000 kilometers. And maybe this wave you could see through the picture, but it's interesting that would mean that there is no viscosity for some reason. There's viscosity doesn't affect this wave, and that's very strange. For example, if I just use 2% of the viscosity of the Mimas bending wave, so it's a tiny amount of viscosity, then I already get the wave damping way closer. And if I use the viscosity of the region, because there are bending waves, there are density waves in the region, and I can extract a viscosity by how fast they damp, and I put it into this wave, the wave damps half of the length that we see, not even half, but it damps almost within the black region. So there's something, there's a reason why collisions are not affecting how the wave propagates, or there's something that is giving it more life as it goes, or it's a mystery. It's truly a mystery how you can get it to be so long. And it's also undeniable from the picture that this is happening. Now, what we're thinking is that this has to do with the fact that the amplitude of the wave and the thickness of the ring are similar. And normally in bending wave theory, there's the thickness of the ring, the ring is taken to be thin, because that's true when you compare it to the amplitude of the wave. But if the amplitude is similar to the thickness, then there are other interactions like this 4 pi g over the thickness of the ring term that actually will affect the propagation of the wave. And we're playing with that, adding that force into the bending wave theory and see if we can use that to explain. But we have a sharp intuition that it does have to do with the fact that the thickness and the amplitude are similar. That this thing can go on forever. And there's another mystery associated, and this was pointed out by this Carreno in his 2013 paper with this bending wave. Here we have an occultation, but here's in counts. So that means that higher means lower optical depth in here because you're seeing less photons. By the way, here, this little kind of wave, you have to zoom in to see that it's a wave over here. Sorry. This feature over here is actually the Janus 7 to 5 density wave. And this damps quicker than, way quicker than the Iapetus bending wave. So if you get the viscosity that you see here, given the damping of this density wave, and you apply it to the bending wave, then you will get that the bending wave, again, damps just within this region. It doesn't go on not even 20% of what we actually see. So there's certainly something propagating this wave in some way. Anyway, there's this bending wave. There's other bending waves in the region, again, with that signal that there's a viscosity that should damp this faster. But also, if you look at the optical depth, there is or at the counts, there's a decrease in light going through here. So there's an increase in optical depth. And that's normally what's being called the inner edge of the A ring. But by looking at the wavelength, the jump in surface density is actually here. So there's this region where there's a high optical depth that doesn't correspond to a change in sigma if we trust the wave to give us the local value for the surface density. So that's also very interesting. And it's also not understood why that may be happening, but we have an idea. First, it could be that, so something that hasn't been included also in the theory of bending waves is that the wave, if you have a sharp boundary like this, and you know this is from wave mechanics, it should have a reflected wave, and we don't know how that works. We don't know how that propagates, if that affects how the things look, if that affects the optical level in some way. So that could be something that this wave is propagating backwards for the reflection and somehow changing the optical depth closer to the planet. And another possibility that we see when we look at the radio data is that there is also this signal that shows that some of the extra optical depth here in this optical depth boundary is actually for smaller particles, just like the Mimas bending wave. So maybe there's maybe self-gravity waves start forming, because there shouldn't be any self-gravity waves on the left side of this plot because we're in the Cassini division more or less, and sigma is small. So you need some critical surface density to start seeing self-gravity waves in the n-body simulations. So maybe the self-gravity waves start appearing here, and that's why you have this increase in signal. And this is something like an interaction of self-gravity waves and the bending wave, which is what we saw in the Mimas case. So this may be a haze. That's the hypothesis. So we have two questions and two possible answers. So first, how does the wave manage to go for so long? And we think that this may be useful for other stuff, for galaxies, for example, or maybe not, but it will be obviously useful for ring physics to know, but it has potential for us learning about how warps propagate in general. And the other thing is what's responsible for that increase in optical depth if it's not an increase in surface density. And we think that it may be something related to smaller particles being ejected also from the bigger particles that accrete them at the surface. And that will increase the optical depth there without increasing sigma, right? Which is what we saw in the Mimas bending wave. There was no change in sigma. That was an assumption for the bending wave model that we use actually. There is no change in sigma. In the signal, it's just created by small particles that are so small that the change in sigma for them is like 1%. So the original assumption holds. And then finally, I want to very quickly mention the Titan bending wave, which is also very interesting. This one you can see it in occultations. But the interesting part is that it has this gap. So the bend is so exaggerated. So it's a 40-degree slope. This one is kind of the opposite of the Hyapetus one, that the ring breaks. And this is interesting because we see in these protoplanetary examples that I showed that when there's the inner disk is too misaligned, you kind of have a gap, and we don't understand when that happens. So if there's a critical viscosity value, and this may be interesting case study to understand why this type of lack of transport here occurs. Here the resonance is at 0, and Titan is very big, so that's why part of the reason also this is so strong. Here's a little model we did with a ray tracing, very simple, of that particular occultation. If you look at this wave in different angles, sometimes you won't see the gap. So the photometry, the geometry of the problem is more complicated than other ways. Right? If you think you have a ray going like this, for example, you will always be seeing some part of the ring. But if you have some other geometry, then you will be seeing the gap. And that makes the problem significantly harder because I use a lot of symmetries to understand and model these occultations, and now I have to be very careful. Here's a comparison, and the first thing that comes that I see is, well, the wave, this peaks in optical lab seem to get bigger and then smaller, and that's not what you would expect if you have the evolution kind of the amplitude to be what it normally is when it doesn't break, which is what we're modeling. And also this edge, it's not trivial. It's not just like it's not just cutting the material. Like there's some material here that shouldn't be here. But surprisingly, on a positive note, the position of the peaks is very good. So the dispersion relation actually seems to hold fairly well, even if this is an extreme case of a non-linear bending. And this is just for completion. This is the last bending wave that it's clearly visible in the rings. And this is this bending wave hasn't been used actually to study sigma. There was a measurement with Voyager, but it was a kind of like a picture that they used to get sigma from this wave. And in Cassini, nobody has tried to do it because there's not as good as a picture. And the occultations, well, the B ring is very noisy and it's hard to get. But if you look at some of the occultations, a very small subset of them, talking about 3 or 4, you can see clearly the bending wave. But there's this here, the peaks, I see them having the proper, or these are troughs actually in the optical lab, having the proper amplitude, but then there's other stuff here that are acting strangely. But if we fit the wavelength, though, we get that the wavelength is smaller than what you will get from density waves, something that we also find in the 5 to 3. So maybe density waves always increase the density measure. You know, there's a theory error there on what the sigma is because density wave changes the density. Or yeah, or something like what's happening in the Mimas bending wave, where I said, well, the sigma is lower because there's motion of particles away from the bending wave. But anyway, the interesting thing is that the surface density of the U-ring, according to this wave, is lower than previously expected. And why that is, also what is this strange structure seen here, is also an open question. Thank you, everyone, for coming.
Thank you very much, Daniel. Very, very interesting. I'm amazed at 20-meter type stuff. Gods, over such a span. Any questions for Daniel?
So I have a question. So you said you sometimes have to hunt to find those waves. Is it, how confident are you that it's really due to a bending wave, or could there be other explanations for the data?
You mean for this one?
No, at the beginning when you had it was very hard to see. It was very low. Which one was that?
Very first slide, or the that had the
No, when it's just, I think before he cut off, or just in
This one.
okay,
Yeah.
yeah. So it says it's very hard to see, it's very faint, right?
Yes.
So how confident are you that it's really a wave, or could there be other explanations?
So for this particular case, so one of the things that truly sells that this is a wave is that the position where these undulations start are exactly where the resonance should be, right? So that's why we think, oh, this is clearly. So the theory is that at 121,000 kilometers, there should be a resonance with Iapetus, and that should launch a bending wave with a certain sigma going away from the planet, because also sometimes waves propagate in, sometimes they propagate out, depending on the resonance. So that's what the theory says. And then we have this undulation that starts right at resonance that goes away from the planet. So that really makes it us think, yeah, this is that
Okay.
wave. Yeah. Normally when we look at waves and if we see some undulatory phenomena, we go and see if there's a resonance there. If there's a predicted resonance there that could be launching a wave. And then in what direction should that wave propagate? And if those things coincide, then we say this is a bending wave.
For sure. Okay, thank you very much.
Sure, good question.
I have a question, Daniel, about what in these regions that you're looking at, like right here, how big do the particles get? Yeah, but and is there like an average particle size?
Yeah, that's a good question. I think I should have talked about that. So the particle size here is centimeters for the Cassini ramp, and then as you go into the A ring, they become bigger. And you have 10 centimeters, 10 centimeter, half a meter particles, average particle size. But this is the average particle size, which in parts of the A ring gets all the way to 1 meter even. So you have like big particles, but then they clump together and they form these gravity waves, and those things are 100 meters long, 200 meters long. So they're in the 100-meter range. Now so we have an estimate for also smaller particle size, and the smaller particle size is also varies, but it's 5 millimeters. We don't really have things that are millimeter or sub-millimeter, and when we do have it, we can actually use one of the detectors to say there's scattering. If you use an infrared detector, here's a good. I actually have this slide. Here, this is a signature. This is a detection of millimeter and sub-millimeter particles in the bending wave. And the reason we know it is that this black line is the infrared beams. So this is the infrared detector, and this is the ultraviolet detector, the green one. And if the infrared detector on average has a higher optical depth, it's because the light is being scattered by particles away from the detector. So this is something we discovered this kind of like 10 years ago. And now we know that if there's an increase in infrared optical depth versus ultraviolet, it's because there's millimeter and sub-millimeter. But this is rare. Normally, what we think, and this is also something we know from simulations, is that millimeter and submillimeter particles accrete into bigger particles very quickly. So you kind of need to have kind of a steering mechanism to actually have them be detected in the rings. So that's for the small size stuff. The big size stuff, we go up to meter size. And then you have the 100-meter structure.
So do you have a structured particle size frequency distribution that has like kind of like a bimodal distribution from centimeters down to fractions of a millimeter, or I'm trying to get a sense of it sounds like you have that there's accumulations in the larger particles, meters or whatever, or tens of centimeters, but below that it's kind of a, you know, would you say it's a bimodal size distribution?
So what people use, so our current best size distribution is a power law with Q equals, you know, minus 3-ish, 2.8, I think it is. Which is what you would expect for things, you know, grinding themselves down. But at smaller size, you have a cutoff, and that cutoff is explained by this accretion process. So that's how people have explained it. And then on the bigger size, there's also a cutoff because there's kind of like a gap between the meter stuff and then the 100-meter wakes. Although the 100-meter wakes are not really particles because they disaggregate in a orbital time period, 2 orbital time periods, right? But you do have things that are big in terms of what their optical effects are. So it's basically when you look at the quotations and you try to do statistics of particle size, you do have these big things creating a big shadow, and then that's 100 meters. So it's kind of bimodal in a way that you have the gravity waves creating the signal, the shadows, and then you have the ring, not clump ring, and that not clump ring has this power law distribution that cuts off at smaller particles.
And the collision velocities are all real low, centimeters per second or something.
They're millimeters, so they're millimeters per second. So they are what you would expect from the thickness.
Yeah,
right?
so when you say grinding, you really mean grinding because they're not smacking. So
yeah. Yeah, I mean the centimeter per seconds are what we see in the bending wave, but you have to get a lot of machinery in there to get those collisions and that ejecta happening. You have to have the perturbation of the moon, and then you have to have the gravity waves and all that to get those collisions to be centimeters per second.
okay, cool.
Yeah. So this is something I thought I was going to show, but this is what when I integrate those equations here, I'm computing the relative speeds and I'm trying different sizes for the bending for the self-gravity waves for the length to 32 meters, 70 centimeters. And this is the orientation. The interesting thing is that if I keep running the simulation, it shows the collisions get this is centimeter per second, right? They get very big. It's 5, 6. So for sure, there has to be some ejecta. Even we have some microgravity experiments where we are throwing, in drop towers, we are throwing things to regolith. And we have done this in space stations. I mean, I'm talking about the UCF group, Josh Cole, which I worked with him. And yeah, they start seeing.
Go ahead.
Pardon?
Go ahead.
Yeah. Even in these experiments, which I think that they are certainly designed that because of the environments, they're going to overestimate that breakpoint where you start seeing ejecta. They start seeing ejecta at 10 centimeters per second when they do these collisions. So we should expect that at the centimeter per second range in general for these gravity waves, which are less packed in together than what they're using, you should have some ejecta.
I was going to say you should talk to Kirby Runyon, who does these collision experiments on the airplanes that do the parabolic flights, and giving a talk last week that, or very recently, that was that showed some of his experiments while they're floating around in there, and it sounds like something that would be interesting for you as well.
Yeah, I mean those experiments, the whole this is a vomit comet or whatnot by
Yeah,
the plane.
yeah.
They actually show that relationship with the, which is what you will expect, that the amount of ejecta depends on the kinetic energy. So that relationship is very cemented, I think, and it comes from those microgravity experiments.
Yeah.